I have essentially opened the microsim.py, that infile generator. So essentially, I am selecting this model. Okay. After clicking import infile, select the model and then choose infile. Here it will tell you how to navigate. For navigating, you will essentially go and select this particular model system function F1 for execution. Model system function F1. Just open this. Whereas you have to go to that and put it into the home folder. Okay. One thing is, for Windows users, please put this folder that I have shared with you into the the folder that comes in the home of Linux, explorer.exe. Okay. Put that into that folder, then it will work. So for Windows users, please put it into that folder, that home folder of Linux in WSL.
So earlier we told you the location. If you are using Windows, you have to use explorer.exe space dot and then it will open a window. So that is the location. There you will see MicroSim, and inside that you have to paste these things.
Pasted it? Huh? Okay, if you have pasted it, then you can essentially navigate now into that folder. It will show up. And once you have done that, select.
For
Ubuntu, you don't need to do anything. Ubuntu, it should directly, you should be able to navigate because all folders are visible. Okay. So select this input iso.in. Okay. Input iso.in and just put open. Okay. It should set and open this particular thing where you are some parameters are already filled up. All right. Online participants, are you able to do? Okay, I'm going to assume that you're going to do. All right. So now the thing is, these are parts of the infile which are already filled up, and essentially I'll tell you what they are. Okay. So first is essentially the dimension of the problem. The dimension of the problem in the infile says it's a 2D problem. That's why dimension is 2. It's filled up. So it directly fills up parameters that get from the infile that I have imported. Mesh x, mesh y, therefore, are the two inputs it will take. It are the x and y dimensions of the problem. Okay. Second is the discretization that I'm using. This is a model system. So it's a non-dimensional alloy system I'm creating. Okay. And therefore, these units are also non-dimensional. Okay. They do not have any dimensions yet. It's there, but it will not be used. So you have delta x, delta y, delta z, which are the three parameters of the three dimensions x, y, z, and delta t is the time step in the problem. So you are numerically discretizing unique finite difference, and the resolution of the discretization is what is shown. Okay. So you click next. Here you have a number of phases in the problem. Anybody has a problem? Just anybody not able to follow? Just louder. स्वप्निल इसको देखना क्या हो You can take square or rectangle here. So in this, it's a rectangular domain that rectangular or square. Download the file into the folder, home folder of Linux in your WSL. So the home folder of Linux you can find in by using explorer.exe command. Terminal में explorer.exe download. If you put it, you will navigate to that folder. Copy from the downloads to that folder. You able to do it? Yeah. Kapil, क्या problem है? Correct. Done, everybody? Okay, so after the discretization of the geometry, you go to the number of phases. We are going to be doing two phase problem. One is solid, one is liquid. Okay, so you can essentially change phase names. I have given alpha and beta. If you wish, you can change the phase names. Some proxy names are given. We'll work with this right now. One is alpha, one is beta. The number of components. Number of components here, it's a binary alloy. So you have two components. Okay. So again, you can change the names of the phases. These are some proxy names given to it: aluminium and copper. Okay. We'll keep it at right now, and we'll go ahead. Here is how long you want to run your simulations. So essentially, it tells you number of time steps you want to run, right? This is number of smoothing steps, and what is the interval in which you want to write. So just for the sake of the time, we will run only for 20,000 time steps, and we'll save every 1,000. So 20 files will be created at the end of the simulation. All right. Here, these are keys for restarting simulations. We will use that later when the time comes. Okay. Okay. Here it comes to material properties. Henceforth is for preconditioning the. You start with a sharp interface. So if you want to precondition, you want to make the transition between solid and liquid smooth, and then start your iterations. So it does some Laplacian preconditioning to smoothen out the domain. Okay, so C equilibrium is essentially that, and C fill is the composition that you are going to fill up the domain with, right? And here also it's the same convention. 0, 0 will be the solid phase, 0.5 and everything will relate to 1 will be the liquid composition. Solid. Of with the last one, which is 1, will be the liquid phase. Okay. 1001, all combinations where 1 exists.
And last one is for the liquid.
All are 1. The next is the slope, thermodynamic slope, and again the same convention, where I am setting the slope of the liquidus. So 0, 0 is the solidus, that is related to the solid, and 0, 1, 1, 0, 1, 1, these are all referring to the liquidus phase. Okay, and here I am going to assume, just for brevity, that both the solidus and the liquidus are equal, which means you have parallel solidus and liquidus lines. Okay. So that essentially is your problem. That's where your thermodynamics goes in. All right. So equal. So essentially parallel solidus and liquidus. Okay. Okay. So let's go ahead. Here is where boundary conditions are set for the different fields phi, mu, c, and we are solving for phi and mu here in the grand potential formula. Huh? Oh. Okay, so I think the online participants, where was it left? Where did they leave?
What was the place where this screen was?
No, 15:7.
No, it was shared. In between it was shared. No, he's just inviting, but you can ask.
So for online participants, when did you stop seeing the screen? After phases and components information. Okay. After phases and components, so that should be the material properties. So here is where we were discussing the material properties. I will discuss one again. Just maintain silence. I am not able to speak. Just keep quiet a little bit. So here 0, 0 refers to the solid phase. So any combination with 0, 0 will be a solid. So C equilibrium refers to the solid phase. Okay. Any combination with 1 refers to the liquid phase. Okay. So all of these will be set to 0.5. Same with the C fill, which is the composition that you fill up the domain with. These are all dimensionless. This infile is dimensionless. Okay. So you are filling with so on 0.78, 0.25, which is the equilibrium composition itself, and so is the liquid composition, which are all 0.5. So your filling composition is the same as the thermodynamic composition, which is the equilibrium composition. And then you attribute slopes, where 0, 0 refers to the solidus phase, and any combination with 1 refers to the liquidus phase. Okay, so these are all set to 0.45, which is referring to a parallel solidus and liquidus combination. Okay. Then we were here. We are solving for phi and mu here. Phi is the order parameter, and mu is the chemical potential. And I am going to attribute all of them as periodic boundary conditions, as is set over here. So here you can essentially set different boundary conditions. So corresponding to the boundary that you click, it will highlight which domain it is, and you can attribute different boundary conditions. Presently there are 2 boundary conditions, periodic and Neumann boundary conditions. You can choose either. I'm putting periodic boundary conditions. Similarly here, x plus, x minus, y plus, y minus. Okay, all of them are set to periodic, and that's what I'm going to utilize. No, periodic boundary condition is a repeated boundary condition. Yes. No, Neumann you don't need to put a Neumann is also, it's a reflective boundary condition. So here it's translational periodicity. In Neumann it will be reflective periodicity. So you essentially reflect the domain about that Neumann boundary. Okay. In the periodic boundary condition you translate. Right? In a Neumann you just reflect about it. So essentially a Neumann, no flux boundary condition corresponds to Neumann, but that is in essence a reflective boundary condition. Okay. What is it? What is it? Corners are not part of the discretization. They actually will not be used for this stencil. Okay. Okay, so now we'll essentially call the domain filling. Here is where you fill up, and this filling has to be corresponding to what I've given in the paper. So you need to fill that part of the domain like that. So your domain is 200 cross 200, and I want you to fill such that it is like that, right? So for this, we will fill up. Essentially, you have different shapes that you can fill up: cube, cylinder, ellipse, sphere. I want you to fill up with a cube because that looks like a rectangle, but you can keep dimensions as that it becomes you can fill the dimensions corresponding to a rectangle. All right, and I want you to fill the solid face. If you fill the solid face in part of the domain, the rest of the domain will be filled with the last face. Okay, so part of the domain is there, and whatever you define as a filling for the first phase, the rest of it will be automatic the last phase. Okay. So that is by definition. So you just need to worry about one phase in the definition. Okay. So here, if I am giving you this phase, this filling combination, you essentially have to fill the cube, and this tells you how to fill. The start point is one corner of the cube, and the end point is the second corner of the cube. All right. So if this is the way it is, what will your starting point be? Okay. One of them is essentially directly 0, 0, 0, which is the z is by 0 by definition because it's 2D. Okay, so 0, 0, 0 is the one end of the domain, and the other end should be corresponding to how much you want to fill up the solid with. Okay, so what should that be? So you may have one of the dimensions is 200. So one of the ways you can do it is 200, some height you need to give. So let's say 10, 0. You can also give 10, 200, 0. Both will be okay. Okay. One will fill in x direction, the other will be filling in y direction. But both will suffice for the type of calculation that we are doing. All right. Okay. So once we have done this, save it. So it will write out one file here, one line here, okay, and that is essentially going to be a first filling operation. Okay, you can keep filling with different shapes. It will come one after the other, but for now we will limit ourselves to this. All right. Hey, by the way, some people have to take screenshots. वो ले रहे हैं क्या? Somebody has to take some screenshots. He's taking. Okay, so then you select the model specific parameters. So again you have to, after here you have to go and select grand potential again. This is just after you fill domain filling, right? And when you click next, it will come to this screen where you have to select grand potential, which is the model selection. Okay, model selection parameters. So here there are several things that will be there. First is a type of simulation. There are two possibilities, binary and ternary. Okay. In principle, you can do multi-component, okay, but the GUI that is present will open it only for 2 and 3. Okay, I'll show you how you can do any number of components. but for the GUI version, it will has only binary and ternary. So binary, and then you have the type of simulation. We will do just an isothermal simulation where the temperature is uniform everywhere. Okay. The right format can be binary or ASCII. Yes. This one. Just click on this. Just click on this and hit text. Yes? Huh? Okay. Okay, so this is related to the simulation type, binary or ternary. Right format is binary or ASCII. We will write what is known as HDF file. Okay, this is a parallel file writing format, which essentially writes, in all of the other formats, the number of processes that you are running on your simulation, you will essentially generate that many number of files. In write HDF file, it's a parallel file writing system where you generate just one file for every time step, although you are parallelizing, and each processor essentially goes and writes its part of the file in one big file. Okay, so that way it's a much quicker way of operations. You don't need to open that many files, and it can be parallelized without any bottlenecks. So if write HDF file is 1, it essentially ignores whatever you put here, which is the right format, binary or ASCII. In essence, binary and HDF file are the best ways to store files in terms of memory, because they are binary by default. Binary files are the best ways to store data if you want to preserve memory. Track progress is essentially telling you how many number of steps you want to store your information, output your. There will be something that will be outputted on the screen while it is running. At what intervals you want to output log data output on your screen. That's what this is. So every 10 iterations it will log out of your, keep logging output on your screen. So this is what you do. These are parameters related to elasticity. It is presently, we are not solving for elasticity, it is 0. Okay. And then you go to phase field parameters. This essentially is a parameter that controls how thick your interface is. Okay, we will come to a little bit in detail what this means. A visualization, once you have simulated it, you will see we can visualize this. All of this will make sense then. Presently, just take it as though they are parameters controlling the properties of the interface. These are parameters that control what is the thermodynamic property of the interfacial energy. Presently, there is no anisotropy, so F anisotropy is 0. Okay, if anisotropy is 0, it essentially means it's an isotropic simulation. All right. So the following properties will make no influence. This is again for present. You don't need to know what this is. This is essentially telling you a particular part of the functional, what its form will be. Okay. There are two value values, 1 and 2. 1 implies a particular type, 2 implies another particular type. So we are using 1. Okay. Here it makes important. Equilibrium temperature is the value that I said. What is the temperature, equilibrium temperature? I am presently setting the equilibrium temperature to 1. Okay, it's arbitrary. Filling temperature is also something that you want to fill your domain with. It is relevant only when you restart your simulation. Presently, it will not be of any use. It can be anywhere. T is important. This is the temperature of the domain that what you want to run your simulations. So if it is 0.96, you are 0.04 below 1. So essentially, you have undercooled or given an undercooling of 0.04 to the system. Okay.
But how we providing this temperature? Suppose there is a regular cavity or something.
It's a uniform temperature that you are putting to the entire system.
Yes, and now pouring something like this one.
You are essentially pouring something which is already undercooled. Undercooled, yes. And you are seeing what will happen. So these are related to certain other parameters. You don't need to touch this right now. And here is the stage where you start writing the input file that you generated. Okay. So please go here and input underscore, you give it a name. So this is W workshop 4. So this is task 1. For task 1, task work 1, task GP1. Okay. So what this will do is, whatever operations you did with your files right now, it will store them into the input file of this name and the filling file of this name after you click generate files. And it will tell you where you want to save it. Save it in the same folder that you had that. It will directly go there, so you don't need to worry. Choose that. So just choose. It will say successfully created input and filling files as the following. Input file saved as input WS4 TGP1. Filling file saved as filling WS4 TGP1. Okay? Everybody until this stage? But automatically it will go to that place only. Everybody until this stage? Okay, so click OK, and here is where your infiles are created. Okay, now we'll keep this guy running. We will not use the run command here because on certain machines it doesn't run. For Windows it doesn't run. Windows it runs. Ubuntu it doesn't run. So what we will do, we'll run it by the terminal, which is universal for everybody, right? So so I will open a terminal here. In this folder where I have created, navigate to that folder where you have created this, and essentially create that. You guys are in the same folder, don't worry about it. Okay, I have navigated to the folder where I need to run, and what I want you to do is I will use Intel compilers, don't worry about it. You guys just run as it is. So MPI run, I think it's visible. Okay. So type this command MPI run, okay, minus NP. This is the number of processors. I'm going to use MPI run because this is MPI parallelized. MPI run minus NP. I'm going to associate number of processors here. Depending on the laptop you will have number of processors different. Okay. For my laptop, I can associate 16 processors to it. Okay. And I will essentially, so my compiled version is somewhere else. So if you put tilde microsim bin, so for people who are doing with Windows first time, just make sure one thing is available to you. That is in your folder CD mount. When you do CD mount, you will have the MicroSim folder sitting there. Okay. In the MicroSim folder, you will have grand potential 2D, finite difference 2D MPI. Can you navigate to that folder after doing CD? Navigate to that folder.
So for the Windows users, when using WSS, so directly run button also would work. Yes.
So if the run button works,
so you just close the GUI. Okay, close the GUI window. Then you will come to the singularity, and greater than symbol will be there. So there, you enter this one. So you have to close the GUI, then you will be able to use the application.
No, first thing that you need to do is to navigate to the grand potential finite difference 2D MPI that you have in your MicroSim folder in your /mount directory. So CD/mount, once you get singularity, go to no, I'm coming to the inside. Guys, just do CD/mount in your singularity, just close the infiles are created. Just do cd/mount after you have opened the singularity bind. With that command is there, no? The singularity prompt. Go to the singularity prompt and type cd/mount. What do you see? You see all the solvers, correct? cd/mount. You are able to navigate cd/mount. Okay, in the cd/mount you will see all the solvers. Now go to CD grand potential finite difference to the MPI. You are able to navigate to the grand potential of. You are able to do CD mount, CD grand potential FDA. Once you have gone there, you just do make. Okay, I am going to do something else before making, but don't worry about it. You guys do just make. Just do make. There will be something comes make, nothing to be done for all. Just do make clean. Yeah, but I am in a workshop right now. They have to wait.
Should we tell them some possible times?
And another 20 minutes.
20.
Okay, make clean, and then you try to do make. Okay, so see what it does. Does it do make? workshop
Okay, who are not able to do this make?
How many are not able to do make? Make done. Make done. So after you do make, if you do ls minus ltr in that folder, you will see that this is this microsim underscore gp, which is your executable, is generated in the folder. If you do ls minus ltr, yeah. No, ls space. MicroSim underscore GP is there. That's your executable. Okay. So once you have that executable, all you need to do is to use this executable for your operations. Okay. That's what I will be doing. So now you can go back for your place, go navigate to the directory where your infile is. Okay, you know where your infile is, you know the folder where it is, navigate to that folder. Once you navigate to that folder, see, I am giving the path to the solver, which will be this only. So for you, it will be one folder up. So for you,
this one I am taking for this executive.
yeah. So for people who are doing Windows, it is in the grand potential in the MicroSim folder. Okay, it is in the MicroSim folder. So if you do tilde MicroSim / grand potential finite difference to the MPI underscore not underscore / MicroSim GP, it should exist. Just check in your singularity. Oh, you're not able to see. Huh? Yes. No, it should be just press only. It should work.
But this will not compile.
This is not compiling. It's just running. You have already compiled. No make. So it's existing. Are you able to find your solver, the executable? Your MicroSim is existing. Tilde/MicroSim exists. Okay. In your home folder, there is a MicroSim folder. Inside MicroSim folder, grand potential finite difference 2D MPI exists. That's what you made now. Inside that, there should be the executable existing. We'll use that executable. Okay, that is what I have typed here. Okay, tilde MicroSim grand potential finite difference 2D MPI / MicroSim GP. Then you follow it up with input WS4 TGP1.in, which is just created, and filling WS4 TGP1.in that you just created. Okay, these are there in this folder. Remember, you are in the folder where you created your in files. That is model system function F1. Okay, and then you put output name, some output name. We'll follow the same strategy, TGP1, and then you have to give the distribution of the workers. I'll give 4 in X, 4 in Y. Okay, so they will multiply to the number of processors that I have given here, 16. Okay, and see what it does. So I will do control minus. It will essentially, to start doing this, where it will, for every time step, it will run alpha, beta, and write down maximum, minimum values for these fields. Can you start to see whether you get this? Output, then you have to give, depending on the number of workers you have given. What is the number of workers, processors you have? Huh? So then you give 2 in Y, 2 in Z, X. Yeah, essentially 2, 2 space 2. You are able to do? What is coming? Did you give the distribution of the processors? Okay. So type out this command, guys. Type out this command. NP is the total number of processors you launch. After giving the output name, which is here, you basically give the distribution of the workers in X and Y. Okay, this must multiply to the total number of processors that you launch. Okay, so type it, give some output name. Output, I'm just giving the output name corresponding to one that we generated. Input file name, filling file name, output file name, followed by number of workers in X, space number of workers in Y. And it should multiply to the number of processors that you launch. Okay, so if I launch with 16 and doing it 4, 4, it can also be 8, 2 or 2, 8 as the case may be. All right. After you have done that, click enter. So in Linux, if there is a command where you don't know the file name, you can do tab. It will autofill the After that, if you put part of the file name and it exists, it will autofill it. You're able to do? It's running? How many are able to run? Okay. Here, run. Running. Running. Back side. Tanmay, what is the problem? Huh? Don't copy the input file. Just navigate it. Be in that directory only. Just navigate to the executable because tilde microsim grant potential. You just migrate. Don't copy anything. Otherwise, it will be non-generic. Go to the folder in which you are in. Where the in file is created. Go to that folder and run. MicroSim is just outside. Don't copy the folder. Otherwise, it will you have to copy every time. Right? Running it? How many not able to do? You're not able to do? What is the problem? Just read out the problem. What is the error?
How to go into the
Huh?
How to move into the folders after singularity?
Singularity is there, no?
Yes, sir. LTR,
LS minus LTR. What does it show?
it should some filling.
Huh? Yeah, you're on the right. You made it, no? You are in the grant potential FPL. So CD minus minus. So now do LS minus FPL. So now you are outside this. Okay. Now where did you create your int file? It's outside this. So ls minus LTR. So where is the place you created your int file? Where did you write that folder? Oh, it's in downloads. This not Windows, no. This. Yeah, this is Windows. That doesn't really matter. So just open a terminal. Open a terminal and essentially go to this folder. Open a terminal there and open Singularity in this folder.
I have to open the terminal.
Yes. And do Singularity bind there. Open a Singularity terminal there and just open it. Done it? क्या हो रहा है देखो? Put a Singularity. Open a Singularity. You know the Singularity bind command, no? So where are you? I was reading. First check where you are. So you are in the grant potential MPI folder. So I want you to go out. So you are in this is the MicroSim folder. That is your in file that you created. That should be outside this. Okay? This is what Windows, huh? Where is it you create an in file? You created an in file somewhere, no? NSM ka hai? That folder you copied, na? Where did you copy it? Oh, this is where you copied. Okay. So this is where you copied. All right. This is your inside. WS task 1 filling. What is the filling? Sure. Okay. So now I am telling you to essentially MPI run minus MP. How many processes are there? Yes. Yes. And essentially now you have to navigate to the executable. You made no make one. Yeah. Okay. So MicroSim. You see, I am not typing everything. देखो MicroSim ये तुम्हारा executable है, ठीक है? And then you give the input name that we have given, input ws-1, filling in, and I'm going to give 4,2 because you have no divisibility is possible. Remember, you have to give output name, output ws 4,2. Okay. MPI, no, there are not enough slots. What? Yes. ये टैब नहीं काम करता है कितना पैसा है तुम्हारा ये कंट्रोल सी कर रहे हैं डबल क्लिक से कॉल हो जाता है वर्कशॉप को ठीक है This is Tanmay. This MPI run is creating an issue. Similarity में MPI run नहीं है क्या? It works. They are in singularity. But slots में नहीं दे रहा? There are not enough slots. No, just try to. No, it's right already. So, Tanmay, just ask him whether he has seen this problem. नहीं वो नहीं हो रहा है. Anybody else having number of slots problem in the Windows? Number of slots not available? Yes, also. Anybody else? When running MPI run command. Number of slots not available? All of you ran? Run ho raha? Windows, you are having number of slots problem. Yeah, what is it telling? Did you do singularity bind here? Tanmay? This problem came before? I think it has to do MP4. MP4 I did 2,2. This is Windows 10. Windows 10, no? Windows 10. Then it should work, no? कैसे कॉपी करते हैं इसको यार? Just we got this. I saw this in a technical file. I think after this I did the WS stuff. Oh. Did you do WFL update? Please do. Yeah, sir. It essentially means that clipboard contains preview. So, lines are getting separated. Ah, I see. We'll retype the line. Minus input this is input WSS filling dot in. There's some problem with it. So this NSF folder is here. CTNSF. So you are in this workshop. Okay. Now your MicroSim is there. You have installed MicroSim. Yes. So I will just do MPI run. Take where is the MicroSim? Where is MicroSim? Where is it installed? In downloads only? Yes. But did you compile it? Yes. Huh? Yes. Okay, so basically I'm navigating to the compiled thing that you have done. And input WS4 and filling WS4, output WS4 just for P1, and I'm giving 4 here, so I'll give 2 comma 2. So basically, you have to navigate to the executable. Whatever folder you are creating the inside, go to that terminal, open a terminal there, open a singularity there, and then get the navigate to the MPI run. We have to give the path to the MicroSim, but that is simple. Till the MicroSim, till the download MicroSim, and then okay. So they will only I use 4. No, but I use 4 for it. I use 4 and how many are having issues? Hello, excuse me. Hello. Hello. Excuse me, just pay attention here once. See, some of you are not able to use the MPI run command. Okay, some of the other issues you are facing. So I'll just walk you through the things once. See, first thing is you have to compile the solver. Okay, some of you had issue there also. So so once you are in the singularity. So right now I am in the as within. Yeah. So first, when you do singularity, bind that command, and then do cd/count. Okay. After that, we'll come here. If you do ls, you'll see a folder structure like this. So go to grand potential, finite difference to the MPI. Okay. So you'll be inside this folder. Then to make. So nothing to be done because it's already we have compiled it. So let's clean it. So this is how the compilation should be.
Anybody having a problem where the compilation has not happened? Anybody?
Okay. So now this is how you have to compile. Okay. Now this has generated some executable files. So MicroSim _GP, write _XCML, and reconstruct. Okay. So these are the executable files which will be required to when we are using the MPI run command. Okay. Now your in files are in some other folder. This is the solver folder. You might have saved your in files in some other folder. Okay. So you have to navigate to that folder where you have saved the in files. So you have to copy these executables to that particular folder. So use copy MicroSim GP. Where did you see it?
In my home directory. Okay. Where MicroSim is there. Not inside that, outside.
Yes. Okay. And just be back. Yeah. Okay. First, I need to find where the in files are. So first I'll navigate to where the in files are. See, pwd is the command to check the file path. So this is the location where I'm at.
My folder, that particular file is in home account.
So your file is in home account. Okay.
In that particular zip file, what we have.
You have zip already. Okay. So we have to copy MicroSim GP /home kill. So if you press tab, it will show what all options, what are folders are there.
So here I have already copied this.
So here Akhil has saved his in file in this particular folder. Okay. So first to check the file location, you have to do this PWD. Then you go to this particular location. See, these in files are already there. Input WS4 TGP1 and this. Okay. So just OS just specify the file path.
Solver का path दे दो. Always navigate to the folder. Give the path to the executor because this will copying business become not in. Okay. Always be in the folder that you are in. In the folder that you have created, and then navigate there. The solver path will be same. Sure. Like in fact,
Yeah. Wait. I'm doing something. Guys, hello. Just wait for 5 minutes, okay? Please don't rush. Professor, please can you say?
professors don't cause commotion. Please.
Okay, I think it's please pay attention. This is just the last step, okay? So I'm telling you how to run the MPI. So this is the path of where our executables are: MicroSim GP, reconstruct, and write XML. Okay. So this is the path. So just make a note of this path. Then navigate to the path where you had stored the infiles.
Always tilde/microsim.
Yeah.
ये पांच जो भी tilde microsim.
Sure. So see, if I do CD, it will go to the home folder. So the infiles are in workshop MicroSim_4. Okay, so now
Model system.
So this is the navigation folder. Go there.
okay, so this is where our infiles are. So we have to copy the executables into this folder.
Copy the key. So directly my
You want to run it that way? Sir.
MPI run.
Okay.
MPI run.
Where run -MP. So even without copying, you can do it this way as well.
Tilde.
MicroSim
Slash. So this will be same for all software. Input
and then
WS4 capital S.
Small.
it's small. Okay, infile and then output.
Filling.
Filling.
So WS2.
WS4.
Output.
Then you can specify any output name. I am just specifying output.
So here
WS4.
we go to
Oh, that's your better. Use 4. Space 2. Okay.
So this is
our
the standard way you will run. Alright. Go navigate to the folder created your infile. MPI run -MP number of processors. Path to the solver is essentially tilde microsim record / whatever. MicroSim. That will always remain the same. Input, filling name, output name, and the distribution of the workers in Excel.
Understood? Any questions?
See, every time you have an infile, you will have infiles in different folders. Just navigate to that location where your infile is. In that location, you just execute this command. Okay. This particular path is the executable. MicroSim grant potential finite difference 2D MPI and MicroSim GP. So this will always remain constant. And then you specify, because you are already in that infile folder, specify the infiles, whatever the name is, and then output file name and number of processors. Okay. And then it should work. So now also, if someone is facing any issue, let us know.
So 2 by 2. Again, what you are doing.
To run this, you always go to singularity or directly.
No, singularity for people who it's better to do with singularity because the environment has all the dependencies between these. Yes. Okay, another important thing. You have to be inside the singularity to run this command. So whatever dependencies are required to execute this command, they are already there compiled inside the singularity. Okay. So this commands will work under singularity. So every time when you start Ubuntu, just use singularity, bind that particular command, cd/mnt, and then do the other things.
Anybody still having issues running it?
And here this 4 are the number of cores that we want to use, and 2 by 2 is because we have a 2-dimensional domain. We are dividing the domain in 2 parts in x direction and y direction. So total, if you have a square, you are dividing in x 2 times and then in y 2 times, you will get 4 cores. So this particular 2 into 2 multiplication of that should come out to be 4. So if you are using NP2, then you can use 1 2 or 2 1. Okay.
Anybody still having an issue running? Anybody? Okay, so I am assuming that you are able to do it. So now we'll just quickly view what has come out from the domain. So for viewing the files, you see there's a folder that will be created where you ran. It's a data folder, all right? Huh? Screen is not shared. It's shared, no? It's shared, no? वो थोड़ा लैग होगा इसके नहीं. Oh, इधर okay. Okay, so for the viewing the files, guys, quiet, please. I have to shout out otherwise. There's a folder called data that will be generated upon running. Okay, that contains the output files. So you can navigate by doing cd data there. It will create, you will see .h5 files. These are binary files. You can't view them directly. Okay? You can't view them. You have to convert them into a certain format. So for converting them, you will use something that is there in that same folder where the executable is. There's something called write XDMF. Okay? Can you navigate? Just type out the command, see if it automatically populates. Tilde microsim grant finite difference 2D MPI, write XDMF, and then type in the input file and the output file that you gave the name to. What is the output name you gave? You need to find out. So best is to go into the data folder and check. So this is what you have, the output name. So just copy the part before the number. And type in 0. What is the range of the file? The first file and the last file, in between which you want to create the .x, what is called the .xmf file. Okay. So I'm going to create 0, 11,000, which is the last 0, 11,000, which is the last file that has run. Okay, and I'll click enter. So it will say processor 0 reading file and finish execution. Is it executing? Just try it out on your computers. Just type out this command, tilde microsim. Don't type out everything, just put to tab, it will come. Tilde microsim slash grandport finite difference 2D MPI slash write XDMF. You should type, it will come. The output file will be the one that you have given. This name has to match. The input file name and the output that you give has to match what you have given. If it's different, it will not work. So go to your data folder first, CD data, find out what is the name. The name can be just found out by the number that is, the name that is sitting out before your this. Okay, and put that here. People able to do? Anybody is having an issue? Huh? Done. Anybody having issue? You guys? Huh? Done, huh? What is happening? Okay, you have to be careful what input file name you give. That has to be the one that you are using. The output file name is also the one that you are using. You should be outside the data folder. You should not be inside the data folder. Yeah, and the name of this file should be the one that you have given for the output file. Okay, if you do that, this will happen. And if you go now to the data folder, you will have generated .xmf files like this. Okay, and now you basically do paraview. Paraview will be there in the Singularity environment, so it will open like this. All right, and now you will be able to see these files that you have generated .xmf. Choose the first one, okay, and do XDMF reader, and you will be essentially having this sort of simulation domain, and what you will see is this sort of simulation. Okay, you see we have given periodic boundary condition. That's why it essentially is acting periodically, so it's going from both ends. Okay, please do until here and then we'll break for tea. Huh? XDMF reader. Able to do? Yes? You're opening paraview? Huh? Opening, huh? Okay. Yourself? There? Nasir, can you just check what they're having? Sure.
So this is so this particular command is used to generate the XDMF file. Okay, this is what you have to use. Okay. Okay, I'll once. Okay, I'll just go through this thing once. See, you have data generated in this particular folder. Okay, so I think most of you have already run this. You got some output data. Okay, now we want to visualize this data. So to do that, so to visualize this data, first we have to convert this h5.h5 file into XMF file. Okay, for that we use the write XDMF executable. So to do that, first, so right now we are in this data folder. Okay, so you have to go outside the data folder from where you executed the MPI run command. Okay, so you did cd space my dot. Okay, so you went into this folder, and this is the folder from which you did the MPI run. Okay, then run this command. This will generate the XML file, which you can see. Okay. Yeah. So in this command, you have to specify where the write XDMF is, which is this particular location. Then the input file name, which you had just used for MPI run. Then the output file name, which you saw in the data folder. Okay, without without the numbers. So just the, so for example, if this is the output file name up to TGB1, okay, that much you have to enter. Then start file, from where you want to convert the data, 0 time, and then the end time, up to what time you want to convert the files from H5 to XMF. So that is what you have to enter here. And then it will show, if it has run properly, it will show processor reading any file. Then he's again going into the data folder, doing ls minus here to see if those XMF files are generated, which are generated here. Okay. Now this XMF files will be using to view in ParaView, visualize in ParaView. So that's why after that you can either go into the data folder or wherever you are, you just enter this ParaView. Okay. So is ParaView working for you guys? Not working, correct? Okay. So something has to be done. Some installation has to be done for this ParaView to work. Okay. So I guess we'll do that after T session. No, because in Singularity, no, it is there. Then for some people it's not working. What is it? So ParaView is not working for whom? Only you. Anyone else? ParaView not working? No. What are we supposed to do? Inside Singularity, at least works.
Yeah, so you are outside Singularity, is it?
Yeah, I mean he's not running through Singularity.
Yeah, inside Singularity. So I'll go and check.
Yeah.
Are we working on? Okay, which file are we working on? We are not able to see anything. WS4. Yeah, for the online, yeah, for the Ubuntu for the online people, we are still on this same thing. We have shared the workshop MicroSim 4. Inside that, you have to go to model system function F1. So we are using this input ws4 tgp1.in and filling ws4 tgp1.in. Any questions among the audience? Working fine?
So everybody running? Try view 12 lines of
Where can I get shop code file?
Everybody able to run into the planar interface problem? Anybody has an issue? Anybody at all? Okay, so online will support.
One person said no, where the interaction is told them.
No, I mean, it's about the info they generate. Name different or something.
No. Where is the location of the?
That is in the model.
Yes, exactly. So that will
The okay, somebody joined here. Okay, better. We'll break for tea now. Okay. After break for tea, we will come back and do the other tasks. Okay. So we'll break for tea for about 20 minutes and then come back. Online participants, we are also going to break for tea, and we'll come back with the in about 20 minutes. So 16:54 is when we come back. So you want to know what to do after that? नहीं उसके बाद अप्लाई करना
Right, happy.
When will we start?
Guys, settle down. We'll restart. We have quite a bit to cover, so we will now quicken. All right. Online participants will restart. Oh, where the hell my help was? Okay, so we'll go to the next task. Okay, first task is I want you to just run the same thing just by changing the undercooling. Okay, we get 0.04, just give 0.06. That means 1 minus 0.06 will be 0.94. So go into the same infile generator that you have launched microsim.py, change the temperature value to 0.94 instead of 0.96 that we did. Do the entire same thing that we did just now, visualize the file and check and see what happens, right? So I just want you to be comfortable running it. Online participants, please try to, okay. Online participants, please start your microsim.py. Aditya, the GUI should be running. You have to open it into the Singularity command. Singularity, you have to first open Singularity and then you have to launch the Python 3 microsim.py. Guys, please settle down. I have to speak much louder otherwise. Okay, so launch the microsim.py and make a change. So here you can essentially go to the model parameters here again and go back here. Here there is this temperature. Instead of 0.96, you can possibly give it 0.94 and go ahead. Okay. And if you want to create another infile name, just to view the file separately. So For example, you can keep this the same and just change this to output T094, right? And you can generate. So there is another way to run it. I will just, if you use this run command, so for people who can run this command using the script itself, there is another way to do it. Okay, if you do run and if you configure the system properly, you can actually run it just by clicking there, and it will run. Okay. But just for a general thing, the terminal one is what we have gone through. If this doesn't happen, just go through the terminal route. Okay. You are able to do, change it and run it. Now you should be able to do it. So it would have finished, and you can essentially go ahead and visualize the same way I showed using the terminal. But there is another way. You can essentially go to somewhere here, which is the MicroSim tool. So if you go into the MicroSim tool, there is a H5 to VTK converter here itself. So you can essentially do it using the. You have to navigate to the data folder. You don't know what is the in file it is asking for. So this and so there is one thing that you have to remember. Please generate the in files before you run it. Otherwise, any changes you made in the in file will not get saved. So even if it is the same name, generate the in file. There's a in the tool there is generate file. Please click on that before you run it. Okay. So here again you can navigate to the place your data is. So we have generated new files now. So T094. So you can click on that, and you can give 0,20,000. Okay, this has to be gone. And convert. So this has to be done twice. And once it's done, you can essentially close it and essentially go here again to the place where data is. First the in file and then the data, not here, the place where the data exists. And you will see VTK files have been created. Just click on the 0th VTK file and you can essentially view the thing here itself. Alright. Now I had forgotten to change the click on generate in file after doing the thing. So that's why I might not see any difference, but essentially the workflow will remain the same. So please try to change the undercooling and run it and see for yourself what has changed with respect to the speed of evolution, or in this case speed of solidification, when you change the undercooling that you get. So I have changed the undercooling from 0.04 to 0.06. See what happens, right? So I've just shown you another way of running it. For people who can launch it in their Windows machines, you can actually do it using the GUI version itself. But in terms of generality, there might be some installations it might not work. That's why we went through the terminal route in the last. Okay, so you can essentially go back here as well. We can look at model parameters, reconfirm what our temperature was. See here, but we didn't save it, so we'll generate files and choose this. Not the data, here. And run. You are able to, okay. What is it? So basically here there is some model parameters. Click on model parameters and you will essentially go like you did before. Go back or go forward here. Here. After model selection, you will come to T. Change this value to 0.94. Give it a different output name, otherwise you will not be able to compare. Okay? So you have to navigate to the folder again, and essentially I have given a slightly different name, which is _1. So we will select this and everything else remains the same. You have to do it twice, and once it's done, you essentially go here. So you will have your 1_VTK, and then you can wish, and essentially you will see this because there are two types of files and it is running a movie over all the files. So that's why the confusion. But it's essentially the naming in the way that identifies. It's the 31 files generated. So the easiest way to get rid of this problem is to delete some of these files and then run it. So it's conflicting with this _1.VTK. So So if somebody notices from last time, this has grown a little bit more inside than before. Okay, that's a consequence of the change in undercooling that you give. So is everybody able to change undercooling and run? What is the difference do you see with the earlier evolution? Faster, right? So that's essentially what I want you to capture. How many are able to run with different temperature? Run. I mean, go through the entire process, run it, visualize it, and then try to interpret what is happening. Okay, online participants, any doubt? Able to run? Anybody able to run? Back there? Able to run, everybody? No? What is happening? So, segmentation fault will only arrive if you have given a wrong name, you are in the wrong directory, and therefore it is not able to find a file. Okay, so it's not able to open a file, and therefore it is giving a segmentation fault. So, check which directory you are in. Okay? Remember, you will have to go to the folder in which your int file is created. Now, put the path of the executable where it exists. Then, input file, filling file, output file, and then number of processes in X and Y. If you miss any of the names, input file, filling file, or output file, it will give a segmentation file. Guys, we have to finish all the tasks before we go. So, you might be there until 10 o'clock in the night if you go slowly.
Always give tab. Tab allows you to get rid of this spelling problem. Able to run here?
Okay, most of you are able to do it. Okay, so if you are able to do it, go on to the next task. And what I want to try is the following. Now change only the in file, okay, just the filling file. Just the filling file. So filling conditions is what I want you to change. Where is my microsim.py? So here is where my thing was. Okay, so let me navigate to the right place. I have too many terminals closed, so I will close the extra terminals so that we are at the right place, and we shall go here again. Okay. So what I want you to do, just a moment. So import the same in file that we just created. Okay, but essentially change the filling. All right, instead of cube, fill a cylinder. All right, and cylinder you add cylinder here. Okay, so navigate until here, add cylinder. They are able to do. Add a cylinder. And the cylinder is at the center of the domain is where you can add. Okay, so instead of the center of the domain will be 50, 50, right? And z, since it's a 2D domain, you will have z start equal to zn equal to 0, and you can give a radius of 20 as is mentioned in the task, right? And save. So it says it will fill the alpha phase at 50, 50 of radius 20. Okay. And then almost everything can remain the same like before. So you can just navigate, and I want you to play around with this t. Start from 0.98, 0.96, 0.94 and tell me what you see with respect to the evolution. Okay, before you do that, you also change one parameter which will be helpful for me. In the material properties, change this gamma to 1. Okay, and return to domain filling and just do this. Go here, So 50, 50 is the center of the domain, radius of 20. And play with this number here, t. I want you to give 0.98, 0.96, 0.94 and see what you observe with respect to the evolution of the cylinder. Okay, this is your task now that you know how to run the solver. Okay.
I ran the first one successfully.
Yes.
From the second one, I don't know what happened.
Yes, because you are running outside singularity. This is singularity nahi hai. You have to do the singularity bind. Otherwise, MPI run नहीं है उसमें.
But ये तो अंदर जाके सिंगुलरिटी में ही कर रहा था.
This is when the singularity was born. So this was singularity bind. If you do, you will get a singularity level. So if it is
So इसके ये सिंगुलरिटी में जाके ही तो ये कोड में गया.
correct, but how are you running MPI run to that?
नहीं.
That terminal, every terminal you have to open a singularity. Did you do run here?
We run here.
Yeah, but the run just if you are doing this, you want to.
No, this is
WSL. Check run what it does.
So on running only, it shoots as error.
Oh, this executable. Okay. The place where your MicroSim.bin is not the place at which you are. It is searching for the executable here, but your executable node is not there.
Okay.
Okay. Can you navigate and look where is your MicroSim?
Sir, actually there was an issue. I was initially doing it.
No, where in terms of the global /home. This is /home. Which one has MicroSim has it?
MicroSim has it.
Okay. Where is the one? So this is the file plan. We didn't compile it today.
So that in MicroSim 2 it might be.
No, if it is in MicroSim 2, then you have to write MicroSim. The point is in that GUI thing, it will search for the MicroSim folder in your home. And if you are using something different, it will not be able to do it.
Okay, let me just run it once here only.
Yeah, you run it with the command line first. With command line you run it. Okay, see whether it runs with the command line. Then everything with respect to the thing should work.
So command line as in I didn't understand. Like
Terminal.
In the terminal only.
Terminal, I'm not talking about why you are doing now. That's a GUI. After you create the ink file, we did the terminal way now. In the afternoon.
This one.
MPI run minus NP.
Okay, that one.
So you open a terminal and execute that command.
Okay.
And see whether it runs.
Okay.
Then you will know that this is properly done.
Okay. So that I did not follow that one, but for that the Ubuntu has to be installed.
No, same thing. Everything is installed. You're in the same singularity thing. Except that I'm not using the run command, I'm using the command in the terminal.
Okay, for that you have to make it, right?
Yeah, making you didn't do.
Making it, actually it was not, it is also not working.
Then you're not in the singularity. Open the singularity. You're able to run for the cylinder? Guys, please start running for the cylinder. You're able to run for the cylinder? So what do you see for 0.98? Huh? Okay.
Just let me run it.
Open the singularity first.
Okay. Here.
That command is there.
Yes.
Yes.
Okay. Now.
Okay. Right.
Now the pipeline.
Yes. No, before you go to the Python. What I want you to check is whether it is compiled.
So this is where your MicroSim folder will come. Why are you running inside this folder? It's never a good idea to do. Where is your MicroSim? Okay.
Okay, make clean we did not do.
It's okay, but make should have not given. So you are in the MicroSim folder now. You do PWE. You are here. Okay, that is your path.
Yeah.
Okay, so now I want you to take me to where your solver is. To no, not solver. The infile is. Where is the infile? NSA.
In a sense.
Here. Right? Which is the input file you created?
Input file we created. Initially, I was creating this one.
Okay, next one that you created?
In SM2.
So now we will run it. So tilde. See, MicroSim is there. Okay. And delete. And then output.
Output also I was giving in SM2.
And then because it's 4, we'll do 2 commas.
So what mistake I was making, sir?
Because you are not in the singularity. Singularity, if you don't put it, all the dependencies are not put. In the terminal that you open, you have to launch singularity.
Okay. So like when I was launching the singularity
Yes.
and then going to directly using that Python thing
Yes.
to come here.
Yes.
So I coming out of the singularity somehow.
Most likely. So, or it is not the right path that is given in that. Okay? Typically, it should not happen. But
Yeah, because first time I ran it completely.
so then you have the thing from which you launched somehow
Shifted somewhere.
Yeah, I don't know how. So typically, it should not have happened.
Okay.
So launch it again. So this is okay. You launch it. We will launch it through the this launch the Python 3. Right? Where is your MicroSim Workshop? Okay. MicroSim.py is inside. It is inside in the.
It is inside the that potential.
Okay. So you have workshop के अंदर what is this? So inside MicroSim you have put the MicroSim Workshop 9. Okay. So typically the solver should be separate. Okay?
So should I show you the actually code?
I can even find out. So the point is what did you do last time? CD program. So outside workshop MicroSim 4 is what this is, right? What is this? This is MicroSim. So inside MicroSim, you have put in workshop.
Inside MicroSim there is workshop.
No, so that is what I'm saying is a bad strategy.
Getting lost in the
Sir, for the cylinder, what parameter you have defined? Middle plane is 50-50.
middle point. So you have to give domain filling 50-50 and 50-50 is the center point.
Okay.
Center of the radius is 50-50. This is 50, 50. This is the center of the domain. 0, 100, 100. Right? And this radius is 20.
So inside CD, inside MicroSim there is NSM, then there is workshop.
NSM,
Then there is workshop.
CD, NSM.
NSM, and then there is workshop.
Yeah, that is fine, but where is MicroSim? This is Workshop.
These are the files that we downloaded, the zip files.
I know. This is so here is where in my NSM. No, where is NSM? Oh, so in MicroSim you have put NSM.
Yeah, in MicroSim there is.
That's why I'm saying NSM that has to be separate. Don't touch the solver.
Okay, I made that mistake.
So don't touch the solver. Solver should be separate, right? So what is the question here? Swapnil, that is not the issue. Whatever number of workers, two issue nahi hai. No, whatever you are typing here. I see. No, it's nothing to do with number of workers. Some other issue. Some other issue.
Earlier, sir, you found that issue. How was it resolved?
That he had made some other error.
Some other thing.
It has nothing to do with. So the place I want to go now is your MicroSim Workshop. Okay. So that is
in MicroSim, then plan potential.
here.
So should I have brought the initial?
No, it's not a big issue, except that it becomes a khichdi here. The solver directly should never be touched. Okay. But why is it not launching now?
It is launched.
Oh, it's not. Okay. Yes, fine. Okay. Now import the infile as we have done. Just see, this is what it is.
It is.
Okay. Now I want you to which is the infile?
Initially we use input arrays.
This is what
Input arrays.
that's fine. Okay, this 100. You give 200 plus 200.
It was the initial one only. I just tried it.
Okay. So center of the domain is 100. Let's put 100 from 100.
Z start and finish.
Yeah, that's fine. Can just give 20.
Radius is 20.
Yes.
Actually, I could not follow from this one.
Say
After
that.
Okay. So 0, 100, 100, 0, 20.
Okay, go into the thing. All fine. And now give different names.
Output also should be
Those are not different names. Just remove our dot out. Just remove dot out.
Acha.
Generate the files. Yeah, it's same. Choose. Okay, it is generated file. And now run. Here it's yeah. So, there is no bin flow. Can we go to a folder? It's able to do the thing, but it's storing it somewhere else. Can we open another folder with Singularity? Another terminal?
Another terminal.
You're able to launch, do the cylinder. What happens at 0.98? Okay, what happens? That's okay. We can do it for different undercools. 0.98, what happens for a cylinder? Anybody run it for 0.98?
So, I want to check that path. Where is it? Can we copy that path here? CD. That error is coming, no?
So anybody run it for 0.98? Here in the, what happens? No, what is happening? Growing? Slowly it's growing. It is growing or shrinking? Growing. This 0.98, 0.96. 0.92 nahi, 0.98. What happened at 0.98? 0.98 is growing. You're sure it is 0.98? Check it. 0.98 is it? No, running is not. I'm asking what does it do? Shrinking or growing? I need you to report me whether it is growing or shrinking. CD.
Paste it. Remove that MicroSim GP. Just put the bin. Yes, enter. Okay. Tell us. It is there. Okay. Survive component. Okay, just do it with the terminal. That is better. It's some strange issue which is particularly to your case. What you do, just here, you go to the place where your folder is there. The inside. It's sort of there here. Just close Python. Here, so this is the job is complete, right? We have generated, right? Now, so what we will do, we will go to NSS. So, workshop. And go here. So, your infiles are all here. Okay? So, we will use npm run here. Just notice this command is universal.
npm run.
And then you just do tilde. Growing slowly or growing slowly or no? You didn't change gamma. What is the value of gamma? Yeah, gamma I put it as 1. Please put the value of gamma as 1. That is the material property. Gamma has to be 1. Okay, not 0.2. Gamma is to be 1. This is where your solver is. Okay, and your input thing is also here. 2.in or whatever. This will always run. Okay? The thing is tilde, MicroSim, whatever. So if you run it with this, it's always generate the infile using the interface, and then
After this, how will I process it in the paragraph?
yeah. So let's run it. It is taking quite some time, so we'll stop it here. So it would have written some files, right? In data, right? Now you have to essentially convert these to XML files. So they are in the same place where you generated the executive. So navigate there. So I'm doing tab. So here you do write XML. Input NSM 2.in, that was your file. And take this as the output name. Output underscore NSM. Okay. And since only 2 files are there, you do 2000. It will generate something. So go to the data folder and now view it. So it will generate. This is happening because of a driver issue with this. We are using Mesa loader drivers here. So the present is not that. So this is the thing that will be. Use the XML reader and apply. Okay. It has used the other file, filling file, that's why it's still planar. And then you can go to the last.
Also, coming before we were creating the files in NSM?
No, nothing to do. Something to do with it. We will look at it later. No, it's nothing.
Okay, for now I can run this.
Yes.
Okay, thank you. Thank you, sir.
Yeah.
So with gamma is 1.98, what do you get? You guys were able to run? With 0.98, what happens? Huh? Gamma 1. Gamma 1, not gamma 0.2.
So we have to slowly. They won't come. I will 6 now. 6 years.
So one thing it is asking is, it is showing is all the values of rotation matrix.
Yes, because you have put anisotropy on. So in your material properties, oh, you have a nice, you have Ubuntu, no? You have put on anisotropy. Fine. 598. They have put this on. If you put this on, you will have to tell what is the orientation of the grain. So you will have to go there. You have to ask you in the it's a static matrix. So this rotation matrix is understood. Okay? It's not there in that file. So it is best if you so you will have to give 0, 0, 45.
So plus and all.
Here it is. Basically, this is where the place. That's for that liquid thing. So, okay, so it will just the solid liquid interface as a rotation. Mouse is next. Where is the okay, it's not a good idea to put the server in there. It files in the server folder outside. So now you can.
So basically, if it is isotropic, we don't have to give any.
But as soon as you put an isotope, you have to do it. Let's see if it launches. Yeah, so it's best run with the singularity. Because singularity doesn't get loaded into the.
Sir, I have to ask something. But sometimes we write precipitation. So precipitation growth and coursing are both same thing.
No. So first is where you have a supersaturated matrix. So you have a growth phase. Once you are growing, you will eating away material from the matrix. So after a while, all the material from the matrix you have eaten away. So then you can't grow anymore. So but then if you have multiple precipitates, depending on the size of the precipitate, each has some capacity to eat. So the larger guy will be able to eat more than this. So because of that, the composition that you have ahead of the interface of this smaller and larger will be different. So there's a gradient of composition that comes because of the size between two precipitates. So then, because of that, there will be flux, and that flux will lead to this guy growing more and this guy shrinking. That is forcing. So you are essentially growing, and now the evolution is happening because of the difference in the sizes of the precipitates.
Yes, both are different things. Precipitation as well as coursing.
Precipitation is a total phenomenon. It involves initial growth phase where you are growing supersaturated matrix, and then after supersaturation is gone, then you enter a coarsening phase where you are essentially growing because of interparticular, and then the grain growth. Grain growth is different. Grain growth is essentially you have multiple grains, and you have evolution by the curvature.
Means I'm going from liquid to solid.
Not liquid to solid. We have multiple, liquid to solid. Let's say you have multiple dendrites. Each colony of dendrite will become one grain, and you have grain boundaries. Each of these grain boundaries will either be curved or straight. So if they are curved, they essentially move in the direction of curvature, and you will have motion by curvature. That's what grain growth is. Again, you will have same thing. Larger grains will grow, smaller grains will shrink.
How do system knows?
What system doing?
That I'm doing.
Precipitation is inside one grain. Grain growth is multiple grains.
Okay.
And both are different phenomena.
Okay. That's why blue one is the solid phase, and then in that some precipitate.
Precipitate is growing. So matrix,
In that input file, where we have to put that? How do we know that this is precipitation we are doing? And
input
this
file nothing knows. You have to specify what the problem is. So if you set up the problem with a two-phase problem, with involving one precipitate and one matrix phase, you will essentially have a precipitation.
okay.
But let's say you have multiple phases involved, involving grain boundaries, that also can be generated. Then you have single thermodynamics. The thermodynamics of each of the phases that you have in the grains are the same.
Okay.
But it will evolve just by convention. That is grain rule. So, yes.
Is there gamma surface energy?
Yes, yes. So what happens with gamma is 1 and 0.98? Huh? 948. Huh? What is happening to 98? Huh?
It's a shrinking.
It is shrinking, right? Now, can anybody tell me why at some temperature it is growing and others it is shrinking?
Because sufficient tender cooling is required. Sufficient tender
Why? Why?
Because latent shift is getting coming.
There is no like this uniform temperature. So this is the classical Gibbs-Thompson effect, right? Because of curvature, the actual melting point of the system is depressed. So it is not 1 anymore. So in a planar solidification front, the equilibrium temperature was 1. But as soon as you made it curve, because of curvature, the equilibrium point is no longer 1. It is actually a smaller value. And you need to be basically giving undercooling more than that value to actually grow. Okay? So if you think about it, it has a perfect analogy to a bubble. If you think about it, bubble is stabilized because of a pressure difference between inside and outside. If you don't have that pressure difference, the bubble will collapse. That's essentially what this happens. You need to provide a driving force for the precipitate as soon as it is curved to sustain itself. Otherwise, the capillarity, which is the surface tension, will lead to its collapse. And the driving force here is coming through undercooling, and you need to provide precisely the driving force required for a particular size to stabilize and treat. So a good part about phase field is this particular aspect comes in naturally in the model, that is the influence of capillarity and the influence it has on the change in the thermodynamic properties is captured naturally. In a classical sharp interface boundary problem where you do not have this description of an interface, you will actually have to impose this as a boundary condition. That is, if you have curvature, you will have to tell the system this is the actual melting point of the system because of the curvature in the system, right? To solve any free boundary problem. But in a formulation like phase field, this is what comes in naturally because all of these boundary conditions are coming in directly into the formulation because it's thermodynamically consistent. Okay, so this is something that I wanted to ask you to do before as an exercise. Now, so last thing, we have 10 minutes to do this. We'll finish by 6. All right. So I want you to try out just one more thing. In the solver, now go to the model parameters. You will go to the solver itself, and I want to turn on anisotropy. Okay, so that it will be solid liquid interfacial anisotropy. So go here. Here. So there is something called F anisotropy. Turn it to 1, which will turn on or switch on solid liquid interfacial anisotropy. And presently you will have cubic anisotropy. Of this essentially gives you the strength of the anisotropy. That means how strongly it deviates from the circular shape that you are drawing now. So if you are isotropic, you go as a sphere or a circle or a cylinder, right? As soon as you deviate from it, you will start to go as a dendrite, which is different from a circle. Extent to which it will grow will be defined by this parameter DAB, which is controlling the strength of the anisotropy. So I am giving you a DAB is equal to 0.02. All right. So I want you to essentially keep this like this and run the simulation. So change this to 1. Okay. It will ask you. So go through the entire process.
until this point, and it will ask you at the end something that I'll tell you what to fill with. So go through the entire thing. Next. It will ask you to fill something. So come to that point and then we will continue. So just when you are about to fill this, I will give it some name, and if I give generate fills, I will give it here itself. You see here underneath, come to the stage, it will ask you something. Please fill all values of rotation matrix. It is asking you this because now you have anisotropy. So your anisotropy can be such that your grain is, remember in the morning I showed you a presentation where one of the grain is rotated like this and the other is rotated like this, right? So you need to give what is the rotation of this fellow with respect to the other. So this is something that you need to fill. So you have to go to material parameters, click on material parameters and phase composition properties. You will see one of these rows is blank corresponding to 0, 1. Okay. Here I want you to fill the following line 0, 0, 45, where I am giving a 45-degree rotation to the 0-degree axis. So if you go 0, it will essentially go as a diamond. I am now rotating 45 degrees, so essentially I am rotating the diamond 45 degrees with the 0, 0. Okay, you can give any arbitrary rotation. Right now I am giving 45. So
I am giving 0, 0, 45.
Yeah, 0, 0, 45.
Why 2 zeros?
You can give Euler angle in 3 different directions. So this is Rx, Ry, Rz. So I am not rotating. I am rotating only over about the Z axis because it's a 2D problem. Okay. Because only solid liquid, 0, 0 is a solid property, so it has to be interface property, so only 0, 1. Okay. Yes? Gamma is 1, yes. Keep it as 1. And you keep the undercooling as 0.94 or something. Or 0.92. Yeah, 0.94 is good. Just keep it as 0.94. Okay? And then run it and see what comes. Remember to generate the in file. If you don't generate the in file, the values don't get saved. Tell this guy to follow the in file which is being done now. nilmoppt.in is not being followed.
That's what he's asking.
We are not using that right. It's not required. Just the general filling. We are generating our own filling document. Just arbitrary cube, cylinder, and so on. Generate your own in file. That's filling file. So today we are doing the slowest. I want by the 5th day that we should be finishing all the tasks very quickly. All right. Otherwise, you don't get your certificates. So what do you get? क्या आ रहा है? Running. Okay. How many are running? How many have gone to the stage of running? 1, 2, 3, 4, 5. Good.
Okay, has it run for anybody quickly? Otherwise, I shall run. So, what do you notice about the speed of the evolution? I mean, how fast is your code running? Is it slower or faster than before? Huh? Did you notice? Still running? Okay. Maybe my thing runs faster than yours. Huh? I'm also using 4. So where has it reached yours? Where has your reached? So I've surpassed you. And the reason is that I'm using a different compiler. I'm using Intel compilers. So Intel compilers run typically faster than the GCC compilers. The only thing is about portability. So that's why. How many are able to put in anisotropy and run? Okay, your code running. What did you observe? You visualize? Okay. As it looks like my code will finish before yours, even after starting later. Okay, so let's have a look. Very good. Huh? Running faster means what? Well, okay, so this is what you see in the terms of the shape of the precipitate. It is not round anymore.
Yeah, and this has happened because you have put an anisotropy in the system. And the anisotropy is a rotated diamond. So if it's not going as a diamond, the diamond is rotated 45, so it becomes a square. Okay? So if it's a diamond, you will essentially grow with 4 arms. That's a typical dendrite. But then you rotate it by 45 degrees, you will get 4 arms in this, and you will get a square. Okay? That's what you are getting right. Alright? So this is what you can do. Everybody able to get until this point? Yes? Who is no? Solve it, huh? Okay. Anybody else? Okay, so we can claim that we are able to run, we know how to run the solver until for model systems and change parameters. Okay. So tomorrow we will see a little bit of real systems, alright, before we go into open form. Okay, so we'll end it here so that we can come tomorrow.
So there is a repetition of what we did today again and again.
Yes.
Very, very similar kind of tasks. Okay. So today is that there is a comprehensive. So if you have been with him also, it should be easier from tomorrow. So we'll start as per schedule 10 o'clock.
So online, okay, so Vamsi, yeah, if I think Swapnil and Tanmay can help you out with the running, you have been able to compile, so I think you'll be able to run as well.
Yeah, I got the.
So online participants will end the thing here today. Tomorrow 10 o'clock we'll assemble again. We'll have one demonstration of a real alloy before we go on to the open form system. Okay. So see you on at 10 a.m. tomorrow. We close. Okay, so let's start. Good morning, everyone, and welcome back to the second day of the workshop. So we'll essentially finish 2 more tasks from yesterday before we go into a description of how to generate CSVs from the TDB. And you will see why we are talking about CSVs. It is essentially related to the extraction of thermodynamic data from databases which are encrypted. So typical databases that you will procure from both ThermoCalc and Pandat, they will not give you open databases in the sense that you can do calculations with them, but you cannot actually see the free energy formulations or the constants and everything. So if you were to incorporate all of that information into your code, you obviously can't do it in a straightforward manner. So we have essentially made a workflow where you extract the required information from the TDBs such that you can recreate the thermodynamic information inside the phase field solver and thereby model the realistic system as it should. Okay, so that is the demonstration. So first, what we will do in the first 2 tasks today is to model them using the model 2 real systems. Okay, one binary and one ternary, where we will be using this workflow, and the third part will be essentially related to how you create that particular CSV for incorporating into your system. Okay, so please open your Python interfaces yesterday. So Windows users, please open a Singularity shell, and in the Singularity shell you can type out the command python3 microsim.py, which will open the interface, and thereby we can get started with the task. So online users as well, please get on with the good morning all the people in the online audience, and please open your Singularity shells on your Windows and Ubuntu machines, and type python3 microsim.py, which will essentially launch your Python interfaces. So please come to this screen that I have just shared with you. All right. So we will now get started. So the first thing is, just like yesterday, we will import an in file which is having almost all the information required by you. Okay. So click on import in file and go to, by selecting grant potential model, you select this thing and choose in file. Okay. So now you have to navigate to the directory which has the in file that we will be using for this task. All right. So this is already shared with you. Yesterday you downloaded that NSM folder. So we will be going into one of the subfolders in that folder itself. Okay. So navigate to that folder. So workshop MicroSim 4, which is the folder I shared with you yesterday. Okay. And in that folder, go to the subfolder, which is aluminium zinc underscore dendrite. This one. Has everybody got it? Yes. Open it. And in this in file, please select input niso.in. Dendrite. Aluminium zinc dendrite, and in that you select input niso.in. Click on that and open. And it will say there are several parameters missing. Don't worry about it. Just click OK. Okay. Have you come to this stage, everybody? Okay, very good. So now we will essentially go through these parameters one by one. So you now know what to do with the meshes. So we will just, for calculation purposes, we have kept it 100 cross 100. If you want, you can increase it to 200 cross 200 if you wish. Slightly more size for the system. So most machines should be able to handle it. Don't touch these information. They are relevant for the realistic systems that we are doing today. If you notice today, we are talking about 1e minus 8. That's the length scale. This length scale is in meters. So essentially talking about the grid resolution, which is sub nanometer. Okay, or 10 nanometers. Okay, so 10 nanometers is what your grid resolution is, and it is because we want to resolve a small feature of the microstructure, which will be of the order of submicrons. Okay, so that's the dendrite tip radius, which we will be simulating today. Okay, so delta x, delta y, delta z, as you saw yesterday, as a grid resolution, and corresponding to this grid resolution, you will have a time resolution that will allow you to do stable time integration of these PDEs. Okay, so these has been optimized, so you don't need to touch them. Then the number of phases are 2, because here also you have solid and liquid. You can also say alpha and liquid. These are the proxy names for the phases that you have. Okay, number of components are also 2, and here you have, these are real components now. Aluminium and zinc are the names. Okay. So we will, just like yesterday, we will run 20,000 steps. We will do 10 smoothing iterations and save at every 1,000, just like we did yesterday. We are not restarting our simulation. Going ahead. Here is where the material properties come. So for alpha, which is the solid phase, your diffusivity is 0, just like yesterday. And because it's a binary alloy, it is by default a diagonal matrix. Okay. The eigenstrain and elastic constant will not play a role as yet here. Okay. Similarly, for the liquid, which is really a liquid here, you have diffusivity only in the liquid because we are doing solute diffusion. So solute diffusion, you know that the diffusivity typically is there only in the solid, and in the liquid, and solid is typically very low. All right. So 1e minus 9 is a typical order of magnitude of diffusivities in the liquid. All right. So that is what we are essentially using. No, this is not this dimensional. 1e minus 9 is 1 is minus 9 meters squared per second, which is this is now a dimensional infile. So we are working with a dimensional infile. Everything is in dimensions, SI units. Okay. So now we go into gamma, which is the surface energy. So this is 0.1, which is the solid liquid interfacial energy. 0.1 joule per meter square. It is a typical value for solid liquid interfaces in metals. Okay. So the R you see is the gas constant, which is 8.314, and this is the molar volume, a typical molar volume, which is about 10e minus 6 mole per meter cube per mole, right? Okay, so next is the functional properties, and here you see, different from yesterday, the function f that we are using here is not 1, okay, it is 4, and this is allowing you to, this function f4 here. So this allows you to do calculations with
by talking to TDBs, okay, in the way that we will describe it. These are important informations, some of them. So the thermodynamic phases are different from the phases that you have inputted. Thermodynamic phases are essentially what are the different types of phases having distinct thermodynamics in the system. So in the methodology that you have over here, the first phases that you input in the place here, phases and components, these are proxy phases, which means you can give any number. But then when you are putting these material parameters here, it is, you are essentially navigating over, you are essentially telling what the thermodynamic identity of each of the phases that you described is. Okay, so here you have to tell the solver how many distinct thermodynamic phases exist in the system. Okay, so for example, here you have a solid which is liquid, and solid which is FCC, and liquid which is liquid. So you have two thermodynamic phases in the system. So therefore you have two. All right. And what are the names of these phases have to be described here. FCC A1 comma liquid. Okay. That means there are two distinct. What is FCC A1? This is the thermodynamic name given in the thermodynamic database that is there in the from the file that we will read from. So thermodynamic databases associate different names to different files, phases. So the name they associate is FCC A1 in the thermodynamic database. You have to use the same name. Okay, FCC A1 is the name. Liquid is the name that is given in the thermodynamic table. You have to use that. The next step is very important. This is the phase map. Okay, and what is the phase map doing? It is telling alpha and liquid that you have initialized. Alpha thermodynamically is FCC A1, and liquid is liquid in the thermodynamic info. So this phase association is very important because it will tell the solver which thermodynamics to use for which phase. Okay, it can so happen you have 3 grams of the same thermodynamic property. So for example, you have alpha 1, alpha 2, alpha 3 liquid, but alpha 1, alpha 2, alpha 3 are thermodynamically all FCC. So then the phase map will be FCC A1, FCC A1, FCC A1 liquid. Okay, so that's essentially the distinction. So you can do multi-grain and multi-phase thermodynamic phases in the same solver. So you have to assume. That is required if you were to do function F2 and the thermodynamic database is open. Here we are talking about the state where your thermodynamic database is not open. If it is open, you have to put function F2 and the file from which it will read will be that. Okay. So presently if it's 4, this will not be used. Okay. Clear? So then we go into phase composition properties, and here the same things that we entered yesterday, we are going to be doing our equilibrium temperature. Equilibrium compositions have to be given, and essentially you give an undercooling to the system for the system to grow. Okay, so here we have chosen the alloy which we have taken has a melting point of 870 Kelvin. Okay, at 870 Kelvin, the equilibrium, liquidus and solidus temperatures are what we are stored here. So just to check for yourselves, I will essentially take you to the CSV file to basically see these values that you are seeing over here. So please navigate in your solvers to this directory, aluminium zinc dendrite. Okay. By the way, this is how the phase diagram looks. This is how the phase diagram is. If you were to plot the aluminium zinc phase diagram, and what region of the phase diagram we are accessing is in this region where there is a solid and liquid in equilibrium. Okay. So we are going to be solidifying FCCA1 from liquid. All right. Okay, now there is a folder called TDBs underscore encrypted in your subfolder, which is aluminium underscore dendrite. So if you go there, open it, and open this file, which is composition underscore FCCA1.csv. Okay, can you all open this? The Windows users I'm more concerned about. Can you open this? Tanmay, that has nano, the singularity nano. Okay. The people who in the singularity shell that you have, there's a way to get to see that in file. So open in the shell that you are in the Windows, just type nano composition tab
you will be able to see something that dumps out of the file. In that shell where the subfolder is TDBs underscore encrypted, can the Windows users confirm? No. In the folder where your TDBs underscore encrypted is, type nano space so you are in the TDBs underscore encrypted folder. No, in a shell, in the Singularity shell. Open another shell. Open another shell where you are in Singularity, and in that shell navigate to the TDBs underscore encrypted folder. Okay, if you're able, in Windows, if you're able to click, go to the folder, if you know where your folder is, right? You know the home folder which Ubuntu is, right? If you were to double click on the file and it opens Notepad or something, then you can watch the file in the same way. If that doesn't work, is the procedure I'm just telling you. All right? So people, there are two ways to do it. If you are in a Singularity shell and you're able to navigate to the file which is TDBs underscore encrypted, the folder, go inside that folder and type nano composition tab. If you're able to do that, this file should display like this. Okay. If you are not able to do this, just type explorer.exe that Tanmay is typing on the board. It will take you to the directory in Windows where that file is. Okay, TDBs underscore encrypted. It will take you to home folder of Ubuntu, and then from there go into the workshop underscore NSM or MicroSim. In that, go to this folder aluminium zinc dendrite, and inside that you will see the TDBs encrypted. Okay, and it will be able to display this. Everybody able to do? Okay, now we are going to be using. This is the information it displays. So this is on the first column, it is the temperature. Okay. The second column is the composition of aluminium in the FCC, and the third is composition of aluminium in the liquid. Okay. And the melting point of this alloy will be the last row over here, where it says that the melting point for this alloy, whose composition is 0.926. 0.816 is the alloy composition. You have melting point of 870 Kelvin. Okay, clear? So this is the C equilibrium solid that we have to check. C equilibrium 0.926, and the liquid composition is 0.8168 that you have to take. So I will round it off to 0.817 and 0.926 in this one. All right. So I can close this now. So this is what you fill like yesterday. 0,0 is solid. So 0.926 is what you fill here. And any combination with 1, you fill up the liquid phase, which is 0.817. Okay. I have anisotropy over here. That's why this column is filled up. Like we did yesterday, 0,0,45, which is that you are giving a rotation about the z axis, because that's the only axis possible here. You are rotating about the z axis by an angle of 45 degrees. You can give any arbitrary rotation. A C equilibrium 0,0 is solid. Okay, that is what I took from that file, which is 0.926. And the next one is C fill, which is what you are filling with. One is equilibrium and what you are filling with. So that is also the same composition. And C guess, so you were talking about C guess. C guess is something that is used in not in this particular thing. It's not too important. It is used for function F2 when you have to iterate over compositions to get things. But this is, you don't need it. Huh? All right. So 0, 0, 45. Everybody clear what is happening here until now? So now you go to next, and there you get boundary conditions for phi, mu, and C. Okay. Presently, they are all Neumann boundary conditions. That means no mass or material flows out of the domain, which is a realistic condition of a closed box simulation. All right. If you want to change it, you can essentially, like yesterday, do NBC and PBC. It will just switch over, and you can select. All right. Then click next, and here is where you want to fill the domain. And just like yesterday, please fill a cylinder at the corner of the box. That means leftmost corner of the box. That is, so you have 0, 0 starting at the left corner. The coordinate axis starts from the left corner and goes away all the way to the right corner, right? So I want you to fill up a cylinder. So click shape as cylinder and add a cylinder over here. The center point I want you to give is 0, 0. That is the left corner. The Z start and Zn are 0 because it's a 2D domain. And I want you to give a radius of just 5. That means 5 grid points. Okay. And once you have done that, click save. So this will appear on your domain filling thing. You can fill more cylinders as and when you wish. Keep clicking this and add cylinder. All right. So once you have done this, you please go ahead and then you go into material properties. So again, say select grand potential and select the simulation type is binary because you have 2 components. We are doing an isothermal simulation, so this will be clicked as yes. Just like yesterday, we are writing the H5 format, so write HDF5 is 1, and we are going to output to the screen every 10 iterations. Okay, that's essentially it. There is no elasticity in this, so elasticity is 0. So this is epsilon, and yesterday, all of you who simulated, you would have seen there is a red something growing, and around it there is something white halo, right? That white halo is the interface. That is the transition region between solid and liquid, and that appears white because you are slowly and transitioning from, you are not transitioning in one step, but you are transitioning in a slow manner from solid to liquid. Okay, and the region, spatial resolution over which you are transitioning is what this parameter controls. So if this parameter is large, that halo will be large. Okay, if it is small, it will be narrow. Okay, typically for phase field simulations which are done properly, you need to have 10 points in the interface. That means 10 grid points should appear in the interface for a stable, numerically well resolved phase field simulation. Now what this 4e minus 8 does is that it imparts for the grid resolution you have chosen 10 points in the interface. Okay, so if you are, this epsilon typically needs to be 4 times the delta x that you have chosen in the infile before. So we have chosen 1e minus 8. So 4e minus 8 is what we have chosen. This will ensure that we have 4 points in the interface. Okay. Okay. The other things you don't need to touch. Here we have switched on anisotropy, which is 1. Okay. And the anisotropy type function, like we did yesterday, is 4. That means we'll get a cubic anisotropy. Okay. And the strength of the anisotropy we are giving is 0.01. All right. Function W, as I said, is a type of potential in the free energy functional, which controls a particular functional form. Presently, we'll use it as 1. And here are the parameters that you've filled up yesterday. Equilibrium temperature for the alloy composition that you have given is 870. So you fill up with 870. But the filling temperature is going to be 857. This is not going to be used because we're not restarting. This is the relevant part, temperature, which is 857. So how many degrees of undercooling we are giving? 13 Kelvin undercooling is what we are giving to the system. Okay. So go ahead, and these are all for certain other purposes. Don't worry about it. And this comes to the place where you will be storing the infiles. So give us name to this infile: aluminium zinc.in. Please be careful what names you are giving, because careful in the sense you need to note what names you are giving. You have to use it for any post processing that you saw yesterday that you need to do. Okay. So you have input aluminium zinc.in, filling alzn.in. So after doing that, please generate the files. It will tell you where to generate. It will take you to the same folder that you are in. Okay. So wherever you are in, wherever you started this thing, you basically choose, and it will say input file saved as this, filling file saved as this. Choose this and click only if it has successfully created. Please click OK. All right. If it has not, it will show you some error file right at the bottom, or error at the bottom. Please resolve that error before you go ahead. Okay. It will already take you to that directory where the in file is. Go there only. Yes, yes. Okay, good. So once it's done this, now what I will do is I will show you by running here, but I want you to run it through the terminal mode that we showed yesterday. Okay, I will do that just to show you how it should look. Your task will be essentially to recreate that using the terminal and the procedure we did out yesterday. All right. So I'm going to click run. So it's running. It will run about 20,000 steps, just like yesterday. Save it in the same folder where you imported it from. It will take you there only. Okay. When you open the choose, when it asks where to save it, it will take you to the same folder where you opened it from. Input and ISO. Yeah, it doesn't matter. Okay, it'll put it. It says it's not there, but it'll add it. So after I show you this, please do it in the terminal mode. Okay, run it, and once you have run it, I will tell you to do one modification to the filling file and rerun it, and we will check what happens. All right. Okay, so it has finished running. So I will essentially visualize it here just for brevity. Please settle down. I cannot shout too much. So we have selected aluminium zinc.in. एक हाथ टाइपिंग के लिए होता है. Okay. So a few more things and then we are there. So MPI run is there, no? Minus NP. For GUI it is fixed as 4. Okay.
In the which infiles? Yes. It will be opening in the same infile where the same directory where the infile you started with. So still save it there. Yes. Okay, there's some issue with this. So we will convert it into XDMF just like we did yesterday. Keep a note of the So open ParaView like you did yesterday. I'll show you what happens and then please reproduce it. That's the best way to do so that you know what you must get. So this is your simulation and this is how it should evolve. Okay. So this is the solid phase alpha plot. The liquid will just do 1 minus out this. So we'll essentially see wherever the solid exists, the liquid will be 0. And conversely, where the liquid exists, the solid will be 0. Okay. Similarly, you can do other things. You can plot the composition and check how it evolves. So this is where it will plot the composition. So you can check what all things to plot here. You can essentially, while doing the line plot only what you need. Okay. So this is how the composition will look. And if you see there are two compositions it selects. Okay. And these compositions will be close to the equilibrium phase diagram compositions that we started from for the 857 Kelvin, which you can go back and check in that CSV file what the compositions are at 857. That is where the simulation is being done. Okay. Okay. So now I want you guys to run it in the terminal mode, just like I done here in the GUI mode, and reproduce this simulation for me. Okay. Guys, please do silently. Just follow the same workflow we did yesterday. So just to revise, you are in this folder, subfolder, right? What you can try to do is your home folder is tilde, okay? Tilde is your home folder. MicroSim will be a folder inside that, okay? Do MPI run minus NP, how many processors you need, okay? If there's 4, you use 4.
and tilde microsim grand potential to the MPI. Microsim GP will exist. This is what you made yesterday. Okay. Give the name of the infile you saved, right? The filling file you saved, and the output file that you want to save. Okay, and then the distribution of the processors. That is 2, 2. If it is 4, it should just multiply to yes. Input file is in the same directory as the directory I saved, sent to you. Aluminium zinc underscore dendrite. The infile should be in that directory.
But you're not seeing it in this microstructure.
No, it doesn't need to be. That's why I'm giving the path to the solver. The path to the executable is here. Okay, and the path will be in your Windows machine. This will be the same path. Okay, all Windows machine people also can follow the same path. Do not copy things into different places. That creates confusion. Go into the directory where your infile exists and give the path to the executable like this. Okay, this will be the same path that you have. Okay, and just click enter. Okay, it will be running in the terminal mode like this as well. स्वप्निल माउस से मत करो तो टर्मिनल से करने दो. Okay. Try everyone to use the terminals for most of the operations. This is how you will be interacting with NSM machines if you were to interact with supercomputers. You will not get a mouse GUI interface. All right. How many are able to run? Fantastic. Excellent. The people who are able to run, can you also view your files? Okay, fantastic. How many are not able to view the files? It's running? Where are you stuck? Huh? Go, Chirantandeep, just go to the folder where the infile is. And the solver is tilde microsim get potential / microsim. Just use there, go there and just Hello, everybody in the online audience is able to hear. If you are able to plot it until this point, where you are able to visualize the composition profile like this. I hope I'm sharing. Yeah, I'm sharing. So if you're able to visualize the composition profile like this, what I want you to check, the next task for you is essentially introduce 4 nuclei at each of the corners of the box that you have. So one at the bottom left corner, one at the bottom right, one at the top right, and one at the top left. Okay, and run the same simulation. So you will just modify the filling function and see what happens. So please run those simulations and visualize what you get. So for running XDMF, you have to essentially, the path to the XDMF is the same as MicroSim_GP. So tilde MicroSim grand potential FD finite difference 2D MPI. Just give the path. You don't need to navigate to the folder. Just give the path tilde MicroSim tab grand potential tab. It will navigate to write XDMF, and then write XDMF. You know the command that you need to give. Don't need to copy anything. Please avoid copying. That complicates matters. You have to keep repeatedly copying otherwise. So whoever is able to do, just run it with 4 at the 4 corners. You need to find out the geometrical coordinates of them. Remember, your box is 200 plus 200. So leftmost corner is 0, 0. Rightmost corner you will be 200, 0, 0, 200 and 200, 200. Okay, these are the 4 corners. Introduce 4 cylinders. The way you are going to do it is, we have added one filling, add cylinder, by adding one line on the thing. You have to keep repeatedly adding add cylinder. It will write input one more line. Again hit add cylinder, one more line, and I'm going to, so 4 lines will be in that domain part of the task here. Okay. So for example, this one I will just show you one more time. So I just want you to modify here. Okay, add cylinder 0, 0, 5. Okay, this will add one line here. Similarly, you add another cylinder 200, 0, 5. It will add one more cylinder. Similarly, add cylinder again 0, 0. Not 0, 0, 0, 200, add, and then 200, 200, 5. So it will add 4 lines, okay, and then you follow the same procedure as before. So once you have done this, you click on this. The other properties don't change. I see. So I will save it as aluminium zinc 4 nuclei. Four nuclei. So remember to generate the files. So choose. It will give input file saved, filing file saved, and then run. Are you able to run? Firewall is not working. Why? Yours is the same problem? Are you in the singularity shell?
Yeah, I am the singularity. Yes, because you have given the wrong name for the XMF generation. Go to your right XMF generation command.
So whenever you open ParaView and it gives the error no scalar texture found, it essentially means when you are putting the right XDMF command, the output file name for the HF and what you are trying to create is not matching. So that check in your data folder what is the exact name of the file, put that itself. If you put any other file, it will create the XMF, but it will have no association with the .h5 file that was created, and therefore ParaView will not be able to execute. Okay?
I have to check in data file.
Data file, check what output name you have given. Okay? There. You have put 3 nuclei only. Huh? It should come. Add. No, put one more cylinder. Add. There should be 4 lines in the thing. I see only 3. Just give me. Oh, you.
Sir, there I see the output data DD1.
This.
I might be getting the same thing. Okay. We're getting that done. Yeah. I see.
Oh, this is and this are the same. Yes, good. So you check your output files. It is very important to use the same output file. So you have DDD1.
Yeah.
This is not the output file you generated. But the output file was just out underscore.
No, this was previous. I did.
No, this is just XMF. There is no HF file.
Okay.
If there is no HF file, it means that simulation did not run. This is the simulation you ran right now. That is the latest H5 files that are generated. Okay. So you have to give out as the in your right XMF.
Okay.
Okay.
Sorry.
So who is having problems with ParaView? I'll solve one of them. So the issue is essentially, what is the error it is giving? No scalar texture found. So you have given the wrong name while converting to right XDMF. So to address that, do this way. That's the easiest thing. So go here, go to the data folder. All right. Go ls-ltr. Okay, it will show you a list of files in the chronology of how it got generated in that data folder. In that folder, you can see the latest file that is generated at the bottom. You will see that is a series of .h5 files that are generated. This is the file that you need to name, that you need to give in the right XDMF. Check whether you are giving this name. If it is not this name exactly, it will create an XMF, but it will have no association with this .hf file that you have generated before. So check this before you go back to the one folder up and execute the right XDMF command.
So selecting the output.
Go back to the, because that's not the file you generated. Go to the, here, no? This is the folder. So, check, come and set CD data. So, aluminium ZL, these are the XMF files. Output underscore ALZN1, and here you are aluminium ZN1. Okay, so the name is supposed to be this. We will create it again just for safety.
What is the earlier command? Here. Infile is correct? Yes. What is the error? No, because it's not selected. This is strange. Something seems to be off in your. You have to apply. This was not. This was not correct. So this had somehow got committed.
Sir, this whole thing is blocking this side. This is not going.
Close it. So just reopen it.
Yeah, I have reopened it several times.
So then you have to close this. There's a paraview issue. Nothing to it. Just when you restart your computer, it will possibly go.
So everybody able to do the 4 nuclei? Yes. Everybody able to do the 4 nuclei? Running, at least running? At least running? Okay, excellent. So what I want you to do once you have done that, you will be able to generate. Let me just convert.
It's not created the XML file. Input.in is the in file. No, I'm very worried about output. And output 0 to 14,000. Yeah, I mean the XML files are not. Okay. There's no filling required. This.
So how many of you have completed? So if you have completed, you can essentially go here and see what you have got. And you will see we have this type of simulation that emerges from the composition field, right? This is what you should be getting, all right? Plot at the composition profiles. You will see that as the composition is moving in, there is depletion of composition here because the thing is growing into the liquid. Okay, so that should happen. Okay, everybody get until this point? Anybody who has not got this? Yes? Got? Anybody not got? Excellent. Now last task with this, which will ensure me that you have understood the entirety of the problem. Change the undercooling of the system from 13 Kelvin that we have given to 4 Kelvin. It will require 2 steps. First, you will have to change the temperature itself from 857 to 866. Alright, that will be 4 Kelvin undercooling. Corresponding to this, in the material properties, you will have to change C equilibrium and C fill by reading in that those compositions from the CSV file I have shared with you. Okay, do these 2 changes, run the thing and tell me what you get for the same filling conditions that I have shared with you. Is it clear in the chat as well? Chat, please get it to this point. You must be able to nucleate 4 nuclei and get them to run there. And now, once you have done this, I want you to run the same thing for 4 Kelvin undercooling. Alright? With the procedure that I just mentioned. Please be careful. That's what you have to change from the CSV file I have shared with you. Choose C equilibrium will not change. Remember, C equilibrium will not change. Even C fill, okay. And you don't need to change any of them. See, just the temperature will need to change. Okay. C equilibrium, C fill doesn't need to be changed. Okay. Just change the temperature from 877 to 866, which is 4 Kelvin undercooling. And just run it. Don't change C equilibrium and C fill. Keep them as it is. Only T. If filling is not required, just T. Yeah, filling temperature also change it. Just change filling and T to both the same value. Nothing. Just this. Just change filling temperature and temperature to 866. Yes.
There is some issue with the paragraph. This output message keeps on coming in.
So this is an issue that once that error appears, this will keep coming. So ignore it for the time being. It's an issue with paragraph.
So then what? Like, how can I move to this level? This is not.
No. It will just you can still view this. Just. It's possible to display this.
Spacing also.
For
the multiple pendrives, you're giving phase as 5.
No. Just 4 filling. Just 4 filling up. It's still a single phase in file. I mean, two phase in file. I'm just giving two nucleus.
This is actually stuck. At night also I was trying.
Do that. Switch off the synchronization. Open the synchronization again. Open the paraview again. See whether okay. It's stuck to that paraview thing. So I will just run through the steps again. This is what I am telling you to do. Choose the same in file 4n.in. Okay, just change domain filling. Domain filling also you can just read in what you have just filled in. You don't have to repeat the procedure. So you can import shape and fill in with this thing that you just filled. So you don't need to repeat the thing. I am just telling you to change model parameters, grand potential. Next, I am just telling you to change just one term here. These two guys from 857 to 866. Okay, that's all. Okay, and run the simulation from there. And run. Just one parameter change, temperature, okay, nothing else. No C equilibrium, C fill is not required to be changed, just temperature. Correct? What change you see? Okay, that is because the undercooling is low. Okay. So this is your last task. Run until 4 Kelvin undercooling, and then we'll finish. Then Swapnil and Arpita will take over, telling you how to generate this CSV. Okay. That is. Huh? Shape has changed because it has grown less, that's all. It will eventually take the same shape. I mean, not the same shape exactly, the dendrite tip radius will be different because it's a function of undercooling. Okay? How much curved it is a function of undercooling. So
every time you were running, I couldn't find the output because it's only showing two files.
Which XMF? Huh?
Yes, sir.
You are giving the file wrongly. I'll tell you.
Yes,
Where's your data? Okay, so your XML files are there, but you see you have done the same problem. This is output one is .hf is the file that you generated, but the XML files you are generating is small output. It's not matching with the .h file.
So that's the problem.
So always navigate first to the data folder, check what H5 file has been created. If this type -NT, it will show you what H5 file got created corresponding to this name.
So that file I can try and
That file H5 will not show up. H5 will not show up. You can't plot H5. You have to plot only XML.
so that file you
Yes, so first you have to convert output 1.xml underscore and 20,000.xml or whatever file. That will show up in Paraview, then you can plot. Okay?
Everybody get until this point? 4 Kelvin undercooling, you will see they are more circular. Okay? And that is because for the grid resolution that you have chosen, it is essentially a round shape. The dendrite tip radius is different. Okay? So this is what you must be able to simulate. Everybody get until this point? Excellent. So we are just in time for tea before we go to the next part of the morning where you will see generation of .csv files. So online participants will essentially break for tea.